All right. What questions do you have? Did I assign anything last time? Okay, that's fine. No worries. I'll probably assign stuff today, but I won't have you turn that in until after the exam. So we're not meeting all next week. Just have to schedule time for the exam. I'll get review posted either this afternoon or tomorrow. Because if I get to it this afternoon or not, I got to write a test. That's first priority because I'm doing that tomorrow. So that'll have to get done first. So, all right. So, been working with groups, doing some different definition types things. I think the last thing that we talked about right at the end of class last time, I think it may have even labeled it as a theorem, but it's actually corollary 7.6 in your book, where if you're in a group, and I'm assuming that the things are in a group in this case, when you do the inverse of a product, it's the product of the inverses, but in the reverse order. And if you do the inverse of an inverse, you just get back to where you started. And again, you've seen these proofs before because they're the exact same proofs that we did in linear for matrices. But just to run through them again, the whole object of these proofs is that we're using the fact that inverses are unique. So in the left-hand side of each of those equations is talking about the inverse of a particular element. So the left-hand side of the first one says, I want the inverse of the element that's created by when I do the A and the B and put them together, right? So the right-hand side says I have something that's equal to it. So what we're going to do is we'll show that the right-hand side functions as the inverse of the left-hand side. And then since the inverses are unique, it has to be the inverse. So when you do the proof of one, to show that something is an inverse, we just multiply it on both sides and see what we get. I better get what when I'm done if it's going to be the inverse. Yeah, so or the identity in groups we usually use an E rather than a 1, but you're right. Yeah, we want to get down to the identity when we're done. Okay. So both of these proofs are going to be identical, essentially. It's just the elements are written in the opposite sides. Okay. What do we need to do first? We'll work on the one on the left-hand side. What do you want to do first? Okay, so how am I going to combine?
Rearrange it so it's like A inverse, B inverse.
I'm going to be a little bit careful with rearranging. If I rearrange, then I'm assuming that I've got commutativity, which I don't necessarily have, right? You're thinking about the right idea by trying to put the elements together that need to cancel.
Just put the parentheses B inverse.
Yeah, let's do that first. Good. Yeah, so let's use the associative property to regroup. And then inside the parentheses now, we get, yeah, so we get the, yeah, usually we use E rather than 1, but yeah, we get the identity. Do I hear Masana?
Morning.
Morning. How are you? Those are your homeworks, by the way.
Thank you.
You're welcome. And now when we have the identity in the middle, how can we simplify that? Whether you do A times E, I always say times, but really I mean the group operation, whatever it happens to be. When you do A times E or E times A inverse, doesn't matter which one you do, what are you going to end up with? Yeah, A inverse, good. I get right. That just becomes itself, and then A times A inverse will give me E again. And like I said, it's the exact same proof for the other one, except that basically the labels have changed, haven't they? Regroup, replace, and then just rewrite all the way down. Notice again, to show that something is an inverse, it has to work on the left-hand side and on the right-hand side. When we say for groups and for rings, when we say identity, we mean two-sided identity. When we say inverse, we mean two-sided inverse. There are structures in which you can have what we refer to as a left inverse, but not a right inverse. Anyway, was okay? All right. So the proof of 2 would look similar. Notice the left-hand side is doing I want to figure out what the inverse of A inverse is. We claim it's just A, but basically that's just a restatement that A inverse is the inverse of A, right? We already know that, don't we? So not only does A inverse function as the inverse of A functions as the inverse of A inverse. It's literally just the fact that we have the inverse, right? So these two statements tell me A is the inverse of A inverse. So therefore, A must be A inverse inverse because we have uniqueness here. And this is true in general. If you're trying to show that something is the inverse of something else, then you just show that it functions as the inverse. When you operate it on both sides, you get back to the identity. That okay? One of the things we talked about last time was order. And order, again, refers to the fewest number of times that you need to operate an element with itself to get back to the identity. When we talk about order, we talk about raising an element to a power. So just to remind ourselves that that's what we mean when you write that, we mean that, right? Just like it does in your usual algebra class, not anything different, right? Or if you want A to the negative n, our shorthand notation, of course, this just means that you're going to operate an inverse with itself n times. And we'll still use our convention that anything to the 0 power is going to be the identity. Using this convention, this is why when we wrote down the definition of order the other day, we said the smallest positive integer, because that's obviously an integer that we could raise an element to get back to the identity, but that's kind of cheating. It's just basically a shorthand notation for the identity. So using these definitions, we have basically your laws of exponents that you talked about back in probably Algebra 1 class, or even maybe a pre-algebra class back in junior high school, depending on when you learned your algebra. What do you do when you multiply? What do you do with the exponents? Add them. Oops. What do you do when you have something raised to an exponent and then you take all of that and raise it to an exponent? What do you do with the exponents there? Multiply them, yeah. Same properties. This works for any group. Notice I haven't been writing down the hypotheses that we have an element in a group because we're talking about groups right now. So it's kind of just standing hypothesis right now that if I write a capital G, I mean a group. If I have an element, I mean it's in a group. Okay. All right. So notice that everything that we've done so far, this is all multiplicative notation. We have additive groups as well, right? In particular, one of our big additive groups that we'll play around with a lot are our Z mod n's under addition. Okay, we'll play around with those a lot because you're familiar with that particular idea, adding integers together, and then of course modding out by a number. But you're familiar with ZNs. It's good examples to play around with, especially when you're playing around with things like order. We'll talk about how we can do order of an ordered pair and that kind of stuff as we're going forward. Okay. But when we have additive groups, this is multiplicative notation, right? When we're writing it as powers this way. So if you know you have an additive group, then your notation will be written additively versus multiplicatively. So what I mean is that if your this is actually summarized on page 198 of your book, if you care. So your operation we write as juxtaposition, AB. If it's additive notation, then we would write A plus B. If we're writing things multiplicatively, so this would be if your operation really is multiplication, or if it's function composition or some other operation besides multiplication, we're going to use E for the identity. But if it's additive notation, we really will use 0 for the additive identity, just like we did with rings. For inverses, of course, we use the exponentiation notation if it's multiplicative notation. But if we're doing additive notation, how do you think we're going to represent the inverse? So the inverse means to get back to the identity. Yeah, it'd be negative A. Exactly right. Good. Because I want to do the opposite of A, right, if it's additive. Exponents, we know that A to the n means that A times times A. If it's additive, instead of A to the n, if you want to operate A with itself n times under addition, rather than doing A to the n, what would you use? A times n, good. Yeah, usually we put the n in front, but you're exactly right. And then your laws of exponents that we just talked about just become basically distributive properties over addition as well. But I just want to emphasize that if you have additive notation, then we won't write our operations as basically exponentiation. We'll do it as multiplication. That's the big thing. It's okay? Hope, did you know your phone's on the floor behind you?
Yeah, I dropped it earlier.
Okay. I just didn't want you to step on it or roll the chair over it. Yeah. Sorry, I just happened to notice it down there. That okay? All right. So let's start playing around with order. So we've already talked about what the definition of order is, but let's see if we can play around with some different types of elements and see if we can figure out their orders. And in particular, I want to start looking a little bit at that permutation group, that SN group again. We haven't talked a lot about it, but a lot of times, well, there's actually a kind of a large theorem about permutation groups in general, but a lot of times when you're looking for examples of non-abelian groups, you want to start looking at your dihedral groups that we talked about, or maybe these permutation groups, because permutation groups are going to be very, very non-abelian. Okay. So to give an example of that, remember the definition of a permutation from a set theory kind of perspective, or from an algebraic perspective that we're doing, is a function, a one-to-one and onto function, I should say, from a set to itself. Okay, and the reason why we call it a permutation is because you think of that as, if I do a one-to-one function of a set to itself, one-to-one and onto function from a set to itself, basically I'm just rearranging what the set looks like, right? But if you think about having like n things to pick up and then put back down again into those n holes, you could take them all out. You could take the first one, maybe put it in the fifth hole, and the second one though can't go back in the fifth hole; it has to go back in some other hole, right? It's basically just a rearrangement. That's why we refer to it as permutation. Of course, my phone wants to try to start blowing up as I'm talking. Forgot to put my watch on Do Not Disturb. All right. Anyway, so we think of it as functions. So we talked just briefly about this notation the other day. So when you have a permutation group, one of the ways to organize the information is to put the numbers 1 through n in the top row, and then where those get mapped to in the bottom row. So this is one way to represent, it's kind of a shorthand way to represent a function. Not next week, but the following week, I think. Yeah, it may be after break. Looking at how much stuff is in the next couple of sections. We'll have even a shorter way to write these things down. We'll have a different way to write these things down. Okay. We refer to that as cycle notation. In any event, what we do have, though, make sure we have to have, is that none of these repeat. We have actual permutations in the bottom. Okay. So this is just the notation. So let's see if we can do a couple of orders of elements of these types of things. Okay. So as an example here, let's say we're in S4. So we have functions that are going from the set 1, 2, 3, 4 to itself. Okay. So let's say we look at what the order of this following permutation is. Okay. So remember that the order is how many times do I have to operate the element with itself to get back to the identity. Okay. What should the identity permutation look like? If in this notation, if it's the identity permutation, you'd have 1, 2, 3, 4 in the top row. What would you have in the bottom row? That's the identity permutation. 1, 2, 3, 4, right? So when I'm done doing this operation with itself, I should see 1, 2, 3, 4 at the bottom, and then we count how many times we had to operate with ourselves to get to there. Okay, that's what we're looking for. All right, so how do we do this operation? Well, remember, this is function composition. So when we do this, we want to go from right to left. I want to think about, so when I write this as a single array, okay, these are my inputs. I want to figure out what they get mapped to as outputs. But I want to work from right to left when I do this. Okay, so start with 1. This says that 1 goes to 4. All right, 1 gets maps to 4. Then I'm going to go and see where it maps to over here. The 4 is my new input for the second one. Where does 4 get mapped to? 1. So 1 is mapped to itself. Does that make sense? What about the next one? 2 maps to itself. Go over here, it maps to itself again, right? So 2 gets mapped to 2. Where does 3 get mapped to? 3. 4 better get mapped to where? Without even doing any work, where better 4 get mapped to? 4, right? Okay, so let's make sure it does. Put 4 in here first. It maps to 1. Go over here. 1 maps to 4. So it really does go to 4. And now we're at the identity, right? So we had to operate this thing with itself twice, essentially, right? Okay. So the order will be 2 in this case. That okay? You might have been able to guess that it would have been 2 to start with. What does essentially that particular that function do? It flips the 1 and the 4. So if you just flop the 1 and the 4 and then you flop again, you get back to where you started. So you probably could have guessed that that was going to be order 2 even before we did anything. Okay. Let's do another one. Say we want the order of 1, 4, 2. I don't know, just making them up. I don't know what the answer is off the top of my head. Now, when we do the shorter notation later, we will be able to check quickly what the order is without doing any much work. Just kind of nice. All right. So again, the idea here, I'm going to take this. It's certainly not order 1. How many elements are going to have order 1? What does the element have to be order 1? The identity. So the identity has order 1, and it's the only element with order 1. All right, so let's do the element operated with itself and see what we get. You tell me where this maps to, the first one. Where does 1 get mapped to? 4. Good. Because notice, again, we're going to work right to left, right? 1 maps to 3. Go over here, 3 maps to 4. So 1 has to go to 4. So before we do the next one, does this have order 2? No. Not the identity, right? Good. All right, how about 2? Good. And 3, 2, and 4, 1. So everybody see where those are coming from? Because you're all reading them off so fast. Feels like I'm going slow today. I can just speed up if you want. No, don't do that. You go plenty fast. Thank you very much. All right. So we're not back to the identity. So it doesn't matter which side you do it on. I usually just keep adding them onto the right. Okay, so I took the answer that we got and added another copy of what we started with. Where does 1 get mapped to? It's like, I don't think it's 1. Where does 1 get mapped to? 2. Good. 2 gets mapped to 4. 3 gets mapped to 1. 4 gets mapped to 3. Okay. Still not back to the identity. Do it again. Oops. If I can make things not so messy. 1 maps to 1. 2 maps to 2. 3 maps to 3. 4 maps to 4. Now are we back to the identity? Yeah. So how many times did we have to do that? 1, 2, well, that was 2, 3, 4. We need 4 copies, right? So the order will be 4. Okay. Is that okay? We haven't talked about this particular theorem yet. We will. remind me again what the order of S4 is. The order of the whole group.
Oh.
The order of S4, the whole group. It's a permutation group.
Oh, it's 4 factorial.
4 factorial is just 24, right? So a theorem that we'll come up with later is that the order of an element has to divide the order of the group. So your possibilities would be 1, 2, 3, 4, 6, 12, 24. So the factor to 24 would be what it would have to be, what are the possibilities. Now, whether or not you hit all those possibilities is a different question. Is that okay with figuring out those orders? Is it okay with playing around with those cycle notations? I'm sorry, I used the wrong word. That is not cycle notation. Cycle notation means something else. Permutation notation. Okay. Cycle notation is the name for the shorthand thing we'll learn later. All right. Anyway, oh my goodness. Unless you want to learn it now, I can teach it now. We'll save us some time later. You're going to have to know it one way or the other. It's not bad. Sure. All right, cool. Good. I like that. I like it. Good. All right, here's how the cycle notation works. So let's just go back to the original one, which was 1, 2, 3, 4, 3, 1, 4, 2. Okay. So instead of writing this longhand, we're going to write it in what we refer to as a cycle, understanding that the cycle is actually representing a function. So when we write this as a cycle notation, I'll start with 1. Where does 1 get mapped to? The 3. Good. So I'll just write the 3 right next door to it. Okay. Now tell me where the 3 gets mapped to. The 4. So I'll write the 4 right next to it. Where did 4 get mapped to? 2. And then the 2 got mapped to 1. Notice that goes back to the beginning, right? So we'll close off the cycle. So this is just a shorthand notation for writing the same function. How many things are listed in that cycle? 4. What was the order of the element again? 4. Yeah, that's not a coincidence. Okay. So let's do one that's a little bit more complicated. Let's say I look at something in S9 here. Doesn't that sound like fun? Didn't look like it. Didn't look like people were having too much fun. Let's make sure I don't mess up. What do I need? Still a 9 and a 5. Okay. So hopefully this will do what I wanted to do. I wasn't paying too much attention as I was writing it down. Okay. All right. So again, start with 1. Now the only way you would not start with 1, and we'll see this in a second, is if 1 got mapped to itself. If 1 got mapped to itself, then we would just close that off. But that doesn't do anything, right? So I would just leave it out. Okay. That's not what happened here, but that would be what, generally speaking, you would do. All right. Where does 1 get mapped to? 7. So I'd write the 7 next. Now you figure out where 7 gets mapped to. 2. 2 gets mapped to 4. 4 gets mapped to 8, which gets mapped to 9, which gets mapped to 5, and 5 goes to 6, and then finally 6 goes to 1, so I'd close it off. This did not do what I wanted it to do. So I'll do another one here in a second. What's missing? 3, but 3 maps to itself. You could write it this way, like that, but again, what we assume is that if a symbol is missing, we assume that it's fixed under the permutation, meaning it just maps to itself. So if the 3 is not there, we just assume the 3 maps to 3. So we wouldn't bother typically writing that piece. It's not wrong to write it. It's just we don't typically write it because we understand that It's not unlike understanding 1 times x just means x, right? There's not a, you understand that there is a 1 in front of there if you need it, but it doesn't do anything to tell you anything, right? You just understand that it's there. Okay. All right, let's do another one and I'll pay more attention this time. However, I won't write nine symbols this time. All right, so let's say we have 1, 3, 7, 4, 1. How about 6, 5, 2. Pay a little more attention this time. All right, again, always start with 1, unless, again, 1 maps to itself, and then you would just ignore it and go to the next one. Does that make sense? Because if you started with 1 and it maps to itself, you just have that cycle that just has 1 element in it, which just means that it doesn't do anything. Okay. What does 1 get mapped to? 3. Then 3 gets mapped to 4. 4 maps to 1. So we close it off. Does that make sense? Okay. Now, did we take care of everything? No. So what's the first thing we haven't taken care of yet? 2 maps to 7, which maps to 2. Close it off. Have we taken care of everything? No. What's the first thing we haven't taken care of? 5. 5 maps to 6. 6 maps to 5. And close it off. Now, have we taken care of everything? Yes. So we're done. That's the cycle notation. We actually refer to this as disjoint cycle notation. We call it disjoint because do you see any cycles that have the same symbol in common? No. So that's why it's disjoint cycle notation. We like disjoint cycle notation for a couple of reasons. One, disjoint cycles commute with each other. Mountain Dew time. I get that. I've had 2 cups of coffee this morning. I've had 2. Never mind. All right. So disjoint cycles commute with each other. What do I mean by that? Well, let's talk about, pardon me. Let's talk about what this now represents a function again, right? So if I would write 1, 3, 4 and then 2, 7, or if I write 2, 7 and then 1, 2, 3, 4, 1, 3, 4, I would get the same answer if I'm trying to do an operation with something. So what do I mean by that? Well, let's illustrate what I mean by how we would operate these things and if they're not disjoint. So let's say I asked you to it's kind of simplify. It's write it in disjoint cycle form. Say we had 1, 4, 8, 2, 3, 7, 8, 1, 5, 4, 6, 2, and it doesn't matter, 1, 8, 5. That looks ugly, doesn't it? It's fun. It's really not bad. It's just having to trace through it. Okay?
3 different outputs.
It doesn't. We're going to simplify it. We think of each piece as a different function that's all been composed together. So it's this composed with that, composed with that, composed with that, composed with that. Okay. Okay, does that make sense? All right, cool. All right, so here's how we simplify it or write it in disjoint cycle form. Again, start with 1 and go from right to left. It's function composition. The rightmost is the inside, right? You got to work inside out when you're doing composition. So my 1 is going to get inputted into this function. 1 gets mapped to 8, right? 8 comes out of that function. It goes into the next one. Do you see an 8 in here? No. So this cycle fixes 8. The only thing it changes are 2, 4, 6. Those are the only things that move. Okay. So 1 goes to 8. 8 stays. This one stays. This one goes to, yeah, that goes back around to the beginning. So 8 goes to 2. All right. 2 comes out, stays at 2. So 1 goes to 2 overall. Yeah. Once you get the hang of it, it's really not bad. It looks ugly to start with, but it's not terrible. All right. So do it this way now. Put in 2, because that's the next thing in my cycle, right? First cycle. Yeah, so it just stays, right? Any symbol that's missing, we assume is fixed, right? Because if I write it down this way, by the way, this would be the longhand notation for that same cycle. Whoops. That's the longhand notation for the 185. Which one's easier to write down? That one is, right? I also can tell immediately that this particular element has order 3. It's a 3 cycle, so it's there's 3 elements in it. Yeah. So this is another reason why we like the cycle notation. Okay. Back to where we were. Fixed. Where does it move to here? 4. 4 goes to fixed, so it goes to 4. 4 goes to 4. 4 goes to 8. Stuff all over me. Okay. Now do the 8. 8 goes to 5. Goes to 5. Goes to 1. Goes to 1. Goes to 4. Yeah. So 4. By the way, we're doing stuff that's in section 5, if you care. This is where I talk more about these groups. But 4 goes to, then to 6 goes to 6. So this whole thing goes to 6. Six goes to 6, which goes to 2 goes to 2, which goes to 3, which goes to 3. Well, there's only one spot where I even see 3 in any of this. Where's 3 going to end up going to? 7. Good. Yeah. Now run the 7 through. I only see 7 in one spot. That's here. 7 goes to 8, which goes to 1. So now we close off. Okay. Now, there's a symbol missing. What's missing? 5 is missing, right? How many total symbols are there, though? Just 8 of them, right? So 5 better be what? Fixed. 5 better map back itself to 5. Let's check and make sure that 5 really does map back to itself. Okay? Run 5 through. 5 maps to 1, which maps to 5, 5, 5. So it really does map to itself. So why would not include it in that case? But if you want to emphasize what you just did, hey, 5 would map to itself. Does that make sense? Yeah. Okay. Again, one of the reasons why we like disjoint cycles, one is, well, we like cycle notation because we can read the order off real quick. Disjoint cycles commute. Okay. So looking again at what do we mean by commute? If I write them in any order, I should get the exact same answer back out again. Okay. So think about it. If I would try to write this and rewrite it again, I would just get the exact same answer that I had, right? And if I flip it the other way around, I'd still get the same answer. They still have the same outputs as functions when you put the same thing in, right? Because if I put 1 into here, it doesn't do anything to it. So it doesn't matter if I put this first or second. If I put 1 into it, it just fixes it. Anything that's, if it's in, try to say this a different way. Any symbol that's not in here is fixed by this one, right? So it doesn't matter if I put it in the front or the back. 1, 3, and 4 will be fixed in the front or in the back. So the 1, 3, 4 cycle does what the 1, 3, 4 cycle is supposed to do, and it doesn't depend on when that 2, 7 is, whether it's in the front or the back, and vice versa. That 2, 7 cycle does whatever that 2, 7 cycle does. Doesn't matter where the 1, 3, 4 is, because 1, 3, 4 doesn't do anything to 2 and 7. So when they're disjoint cycles, you can write them in either order. Okay? Yes?
In the previous question, what would the order of that be?
That was the next question. Good question. Cool. All right. So if they commute, well, you know that the order of this is what? 3. And the order of this would be 2, right? So do you have any guesses on what the order of this might be? 6. How'd you come up with it? Multiplication. Yeah. So notice that if I raise this particular element to the 6th power, that means operate each one with itself 6 times. If I operate this one with itself 6 times, well, after 3, I get back to the identity. If I do it 3 more times, I'm back to the identity again, right? Likewise for the 2. If I operate that cell with itself twice, I get back to the identity. Do it 2 more times, I'm back to the identity. 2 more times, I'm back to the identity again. And nothing in between works, right? Just because I get an element to the 6th power gives me the identity doesn't mean my order is 6. It means my order divides 6. We'll prove that here in a minute. Now, probably longer than that, but it'll be today. Okay. All right, let's go. Okay. So along those same lines, what if I asked you, and see if you can come up with this one? Pardon me. Let's say we had one. Where my problem is, I don't have enough symbols. 1, 2, 4, 8, and let's say 3, 6 to start. Let's do that one first. So again, let's think about it this way. We know they commute. So if I need to do a power of that element, I can distribute the power to each piece since they commute, right? So what's the order of the first cycle? And the order of the second cycle is 2. Now, what's the smallest positive integer that you need to use to make them both get back to the identity? 4 will work, right? Because 4 is a multiple of 2, so I don't need to get to, yeah. Good, exactly right. Yeah, it's going to end up being the least common multiple. That's exactly right. Yep. Yeah. So let's say that, or a lot of times they use Greek letters for permutations. So let's say your order of alpha is 6. Your order of beta is 8. Your order of gamma is 9. You want the order of alpha, beta, gamma if alpha, beta, and gamma are disjoint permutations. What I mean by disjoint permutations is that if a symbol appears in one of them, it doesn't appear in the other 2. Okay. I have to be careful because if they're not disjoint, then they don't commute typically. They might, but they don't have to if they're not disjoint. And then I can't do that, distribute the power over each factor. Okay. What do you think? Yeah, 72 is the least common multiple, right? It wasn't a great example because I just needed to look at the 8 and the 9, and then 72 would work for the 6, right? So the least common multiple of alpha, beta, gamma is 72. So be your order of alpha, beta, gamma. Again, these have to be disjoint in order to be able to do that. And notice I didn't write them out because I didn't want to have enough symbols to try to make them disjoint. Once you get above 9, then you have to start putting commas in your cycles to determine if you mean 11 or a 1, or sorry, maybe a 12 and or do I mean a 1 and a 2? Right? So once you get above 9 symbols, then you start doing double digits, and double digits make things messy in cycle notations, and then you have to put commas in. So anyway, this okay? So let me show you just for a second of what I mean when the disjoint cycles don't commute. So what if we did 1, 2, 3, and then did 1, 2 on this way, and then do the same thing the other way around? In the first one, where does 1 get mapped to? 3, right? Because 1 goes to 2. Put it in the second one here. 2 goes to 3. Where does 3 get mapped to? 1, which means what must happen to 2? It maps to itself. Does it really map to itself? 2 maps to 1, and it maps back to 2. So it is fixed, yeah? What about the other way around? What happens to 1? It maps to itself, right? First cycle, 1 maps to 2. Take the 2 out, it maps back to 1. So 1 is fixed in the second cycle. In the other one, 2 maps to 3, and then 3 maps back to 2. Did we get the same answer? No. Okay. So these are not the same thing. And by the way, you can use this exact same setup to show that any Sn is not abelian. Literally use 1, 2, and then use the cycle 1 to n. If you use the cycle 1, 2 on this side, it's fixed. If I use the cycle 1, 2 over here, well, 1 maps to 3 every single time. So you can't have the same output. Right? So if you do 1 through n, and then a 1, 2 on the right, 1 gets mapped to 3. But if you do a 1, 2 on the left, and then 1 to n, 1 maps to itself. So they can't give you the same answer. Which means that every single Sn, when n is bigger than 3, bigger than or equal to 3, is not abelian. Every single Sn. Well, what is S2? Not very interesting is what S2 is. How many elements would S2 have? 2. It's either the identity or the permutation that flips 1 and 2. Guess what? That's the same thing as Z2. Because either you flip 1 and 2 or you don't. What are your elements in Z2? 0 or 1. And if you think about a computer science idea, 0 is you don't, 1 is you do, right? Okay. So kind of this, it's literally the same exact structure. What's that? What'd you say? Sometimes. So
sometimes 0 just means it's positive.
Sure. Or in the Z2 example, 0 means it's even. And 1 would mean it's odd. All right, anyway. Too early for this? I'm sorry.
15 minutes until I have to do this anyway.
Had what?
So, but for by 15 minutes till I have to do this anyway.
Oh, sure. Gotcha. All right, so let's do some different theorems with order. This is theorem 7.8. One says that if A has infinite order, then all powers of all powers of A to the K are distinct. Forgot the word all. Assuming that K is some integer. Okay. Let's think about why. What would happen if they're not distinct? Well, if we have two powers of A that give you the same answer, where K and L aren't equal, what can I do on both sides to get the identity on one side? Let's suppose that you're, just for argument's sake, rather than not being equal, let's say your K is strictly bigger. One of them, if they're not equal, one has to be bigger than the other, right? We agree? One has to be bigger than the other? Okay. So what can I do to this equation to get the identity on one side?
Subtract A to the L on both sides.
So I think you're thinking about what the idea, but we want to make sure we have the identity and not necessarily zero. So rather than subtracting, if I wanted the identity of the group, what I want to do. So
Or
multiply by the inverse. That's what I'm looking for, right? I would multiply by the inverse of A to the L. The inverse of A to the L is going to be A to the minus L, right? That would be the inverse of A to the L. Okay. So I can write this as A to the K minus L equals the identity. If K is bigger than L, then what can I definitely say about A to the K minus L? It's positive, right? Agreed? Okay. So if I have, pardon me, if I have two distinct powers of A that give me the same thing, then I can raise A to a positive power and give me the identity. What does that say about the order of A? Can it be infinite? No. Remember that the order of an element is the smallest positive number that gets me back to the identity. Well, if there exists a positive number that gets me back to the identity, there has to be a smallest one. That's a well-ordering principle idea, right? So this would imply the order of A to the K, the order of A is finite. Which gives you actually part two of the theorem. They're related, obviously. If A to the I equals A to the J, where I is not equal to J, then the order of A is finite. I mean, that's the argument. Okay, so as you raise higher and higher powers of an element, if you eventually, well, actually it's kind of an I'm going to say it this way, but it's not really what would ever happen. If you raise an element to higher and higher and higher and higher powers, and eventually you end up back to what you started with, the element, you must have hit the identity along the way, is what that's saying. You must have hit the identity in your whole group of powers, and so you had to have a finite order. Otherwise, you're just going to generate an infinite list of things. Does that make sense? All right, so a couple of other proofs that go along with this. This is theorem 7.9. The first one says that if you raise an element to a power and you get the identity, the only way that could have ever happened is if the number that you use divides the order. Notice it doesn't say it's equal to, it just says it has to divide the order. Okay? That makes sense, I think. Okay? So remember, you've probably done this a while ago, where you've done powers of I. If I can write them down. And you keep going in that cycle of 4. You've probably seen that with the powers of I before. Well, how did you know how to simplify that? Well, you noticed, oh, look, my multiples of 4 all got me back to 1. So really, I just needed to divide by 4 and look at the remainder. The only way you could have got back to 1 is if the remainder was, what? 0, right? Exactly. The only way you can get back to 1 is if the remainder is 0, or you were a multiple of 4, which was the smallest power of I that got you back to the identity. Right? When you played around with simplifying those things, that's exactly what you did. So the only way you can get back to 1 is if you're a multiple of 4. This is exactly what this is saying over here, just more generally for groups. The only way you can get back to the identity is if you're a multiple of the smallest thing that gets you back to the identity. Okay? This relates to kind of stuff that you've seen before, right? So what's the proof? Just to simplify notation, let's say that the order of A is n. Now, what did I just say just a minute ago? You knew that the only way that you got to 1 when you raised I to a power is if you divided by 4 and got a remainder of 0. So the whole proof of this is going to be divide the order, try that again, divide the power by the order. Okay? By the division algorithm, there exist unique Q and R such that K equals NQ plus R with R being at least 0, but strictly less than N. That's division algorithm, right? I've used the notation with the exclamation point for there exists a unique. Yeah. Just making sure. I hate throwing in new symbols and not telling you what they were. Okay. So we're assuming that A to the K is E. We're doing the left to the right. The right to left, hopefully, is pretty obvious. But we'll do it in a minute anyway. If A to the K is E, then we have A to the NQ plus R equals E. Let's look at how we can rewrite this little piece here. Since there's a plus sign in the exponent, how can we separate it? Times I hit the R, good. It'll be times, exactly. And then when you have that A to the NQ, I can also pop the Q up, right? So we can write this as A to the N to the Q times A to the R. right? Do it that way. N is the order of A. It's what with the notation we use for the order of A. So what does A to the N equal? Well, E, yeah. it's E, right? A to the N is E. E to any power is going to be E, is the identity, right? Raise the identity any power. So all we get here is just A to the R equals E.
Wait, can you explain why A to the N is? Oh, because.
Yeah, because that was what we're using for the order, yeah. So remember, the definition of order is the smallest positive integer that gets us back to the identity. So, yeah. Okay. All right. So that's actually important. I'm glad you mentioned it. Ooh, getting cold finally? Hope will be happy that you're now cold too.
Yes.
Right? All right. So that was a good point though. The order of A is n. That means n is the smallest positive integer such that A to that power is E. What is the relationship between R and N? R must be less than N. So can R be positive if N is the smallest positive? No. So what must R be? 0. Yeah, exactly. So since the order of A is N and R is strictly less than N, we see, I can write the right letters, we see that R has to be 0. Well, if R is 0, oh crap, I wrote the theorem backward. I gotta fix it. My theorem, it's backward. And I knew it was backward too. Crap, I'll fix it in a second. What does that say about the relationship between K and N? It's the other way, right? It's N divides K, right? That's just why I said I have my thing written backward. And I knew that. Sorry. It has been a week. Pretty sure this week's been like a month. Okay. Which is what we wanted to prove. Shockingly enough, if I write the theorem correctly, that's what we wanted to prove. Okay. All right. The other way around. So again, we did the left to right. The right to left, hopefully, is pretty straightforward. If your N divides K, if N divides K, then you get what we just said a second ago, didn't we? This would be the other direction. This is the shorter direction. Okay. So again, just to make sure I emphasize this, especially since I wrote it backward. If you take an element and raise it to a power and get to the identity, the power is not necessarily the order, but it has to be a multiple of the order. Now, if the power you use is prime, and you know the element's not the identity, then that has to be the order. So for example, if you know that A to the 5th is the identity, and the A is not the identity, then you know that the order of A has to be 5. That makes sense? Okay. All right. A couple of other little results here. Oops. Try that again. 2 powers of A are equal if and only if when you subtract them, they're divisible by the order of A. Write it that way. That's just, I'm not going to write it on the screen. That's just a restatement of the first part. We just did this a minute ago. If A to the I is equal to A to the J, You can move the A to the J to the other side. And now I have a power of A that gives me the identity. So the order has to divide that subtraction, which is exactly the result. Right? It's literally what the result is. Okay. 3 says that if, the order of A, if the order of A is divisible by D, then I need to make sure my D is positive. Then the order of A to the T is D. That kind of makes sense, I think. Because if I raise A to the T to the D power, you would just bring the D down. Actually, pardon me, we can say something a little bit stronger. It says if the order of A is n, then the order of A to the K is n divided by the GCD of n and k. That's actually a little bit stronger, isn't it? What we just wrote. Think about why that's true. Just with it, rather than going through a big long proof of it, let's just think about why that has to be true. Okay. Let's say we know that the order of A is 15, and we want to know the order of A to the 6th. Well, notice that this left-hand statement says that A to the 15th power has to be the identity. Agreed? Notice that when I break this up in this fashion, I have A cubed raised to the 5th power plus still the identity, correct? So notice that if something has a 3 in it in my power, and I raise it to a 5th power, I'm going to get a 15 in it, which will send it back to the identity, right? So let's go over here. If I have A to the 6th, that's A cubed, and then another A cubed, right? Essentially. I guess I could have written it as a 2 times 3. Doesn't matter, right? But notice it's got an A cubed in it. So if I raise it to the 5th power, I'm certainly going to get back to the identity, right? Because I'll get a 15th here and a 15th here when I raise it to the 5th power, right? Will anything less than 5 work? Well, no, because I have an extra 3, right? Notice I have to cycle this back on 15s, don't I? If I try to do something less than 5, it's not going to work because I'll get what? That would be a 4, and that would be a 4, and have something. Try this one. This will be a 24th power if I use a 4, right? But it's not a multiple of 15 because I have to get back on the 15s, right? If I try a 3, it'll be an 18. That doesn't work. If I try a 2, it'll be a 12. But I need that. I need a 5. I already have a 3. If I combine it with a 5, it works just fine, right? So notice that the order here will be 15 divided by that GCD, which is 6. The GCD of 6 and 15 is 3, isn't it? It has a 3. I don't need the 3 anymore when I do my powers, but it doesn't have a 5 in it. So I definitely need a 5 in my power to get back to the identity. Okay. So if you did another one like order of A is, let's say, 240, and you want to know the order of A to the 45th, say. So the first thing you would need to do is do the GCD of 240 and 45. Well, they both have a 3 because they're both divisible by 3, and they both have a 5 because they're both divisible by 5, right? So I think we get 15 as the GCD. Well, so what does that mean? The A to the 45th already has a 15 in it, right? So I just need to put it with the other factor that gets me up to 240, and I'll get back to the identity, right? That's what that tells me. So the order will be 240 divided by the 15, which gives you 8? No, 16. Try that again. Which makes sense, because notice that 214 has a 16 in it. This has no way to use that 16 to get back to the identity. I need 16 powers to be able to do that. Does that make sense? A little bit? I mean, we didn't do the proof, but this is how you would do that. All right. Let me give you some problems to work on. 201, 5, 10, 12, and 16. Like I said, don't worry about it until after the exam for turning it in. Even that next Thursday is fine. But I figure you probably want to concentrate on looking at stuff for the exam this next week. So, all right.